Hello, good afternoon. My name is Pedro Restrepo, and welcome to the seminar that we will be giving in collaboration with the USGS, Skip Vecchia. It is just a couple of minutes after the start time, so let me get going. The purpose of this seminar is to discuss the results of our forecast, the 2013 forecast of the Red River of the North, and try to seek input from all of you in areas where you may have already some expertise or experience with similar cases, or with some of the symptoms that I'm going to present. So the outline of the presentation is, first, a brief introduction to the North Central River Forecast Center. Then I will talk a little bit, very briefly, about the Red River of the North. The third point will be to do the past forecasting and the performance. And finally, I will discuss the 2013 snowmelt season. So let me start with the NCDC. We are one of the 13 river forecast centers of the National Weather Service. The 13th one is here, the Alaska River Forecast Center, that, well, it is not shown because if it is shown, it will take half the map. Our area of responsibility are three major basins: the Great Lakes, the Hudson Bay, and the Mississippi River drainage, which of course goes to the Gulf of Mexico. We issue forecasts on 426 points, and to do that, we have to model 1,173 subwater sets. Let me talk about the Red River of the North. The Red River of the North has about 40,000 square miles. That may be a little bit smaller when Devil's Lake, which is here highlighted in blue, is not contributing. But right now, the Corps of Engineers is pumping water from the Devil's Lake into the Cheyenne River Basin, and therefore it is a contributor to the Red River of the North. I use a little bit of topography here to highlight something. You see topography, you know that this area is fairly flat. But in the area of the Red River of the North is as flat as it can be. And that's one of the challenges that we have for forecasting on the Red River. This is a slide that was provided by Rick Kohler at the Weather Service office in Boulder for the COMET program. And it is kind of striking. It shows how the higher flows on the Red River, when they happen, and the magnitude. The magnitude is proportional, or the size of the marker is proportional to the amount, to the crest value. We can see that there are actually two areas. One cluster around March, April, another one in the summertime. Clearly, those are the snowmelt crests, and the other ones are related to major summer storms. We can also see that the most recent crest was the latest one on record, since we have been having records on the red of that magnitude. But we can also see that the crest is a very clear tendency to having higher values the years become more recent. So there is a tendency to increase values of the flows. And it is just not of the crest, but here we see the flow duration curves by decade starting in the 1950s through the 2000s. And we see that up until the 1990s, all of 1980s, all of the flow duration curves were kind of clustered in a single place. However, starting in the 1990s and 80s, we see an increase at all ranges of values. This scale is logarithmic, so you can appreciate that better. And Skip Vecchia in his presentation will talk a little bit more about the increases in the flows on the Red River and the possible causes for that. Well, let me talk about the past performance, and let me start with the 1989 flow forecast on the Red River. We have here the observed flows and the raw simulated flows. This is not the forecast; those are actual simulations done recently based on information that we had at the time of this flood. The NCRFC was not still using the systems that we have right now, but this is what would have been had it been done today. And the performance at the time was also quite good. The flow on the left-hand side shows that the forecasted or the simulated value was about 16,000 CFS, and the actual observed value was around 18,000 CFS. And I want you to keep this forecast in mind. We will come back to it in comparison with the 2013 forecast. We have here the forecast in 2006. We have the raw observed flow, which is the green curve here. The blue is the observation, and the gray or white is the official forecast. The official forecast is issued by the forecaster actually manually changing some of the values based on past experience and how it sees the crest developing. You can see a very accurate forecast, and the peak flow was around 20,000 CFS. The 2009 was one of the most recent that gave us problems. And here I don't have flow, I have the stage in feet. The first value was forecasted quite accurate. The second peak was missed by about 7 feet or so, 6, 7 feet or so. And that's one of the first indications that there's something on the red that we just don't quite understand. That the Sacramento model and the Snow 17 model that is used for snowmelt do a reasonably good job, but in some cases it just goes out of where the range of comfort forecast is. And then we'll go to the 2013 snowmelt forecast. Again, we have the flow in about 15,000 CFS, 16,000 CFS observed, and our forecast was about 27,000 CFS. Notice that the rising limb of the hydrograph was not badly forecast. It was pretty good forecast. But while the model kept indicating an increasing flow, the flow on the Red River stopped. And that is one of the things that I want to discuss with you. Notice also that the volume that had been forecast was considerably larger than the volume of water that was observed. So let me discuss the snowmelt season. We have a map of the snow water equivalent between 2013 and 1989. In red, 1989, in blue, 2013. Notice that by and large, in many cases, we have up to twice as much water in 2000 snow water equivalent in 2013 than the one we had in 1989. So let me put both hydrographs together and let's see what happened. They happen on different dates, so I don't have a date at the time, but I just try to superimpose one next to the other to be able to appreciate the differences. The dashed line corresponds to the actual observations, to the actual simulations, and the solid lines correspond to the actual observations. So we see that in 1989, which is the blue line, the crest was about 18,000 CFS, and the crest during 2013 was about 16,000 CFS. The puzzling factor for us is why, when our models on the forecast slightly the crest in 1989, for 2013 it was so far out from where it should have been. And we have gone to done some research. We have had some conversation with the soil scientists at North Dakota State University, trying to understand the processes that are going on the basin, and that we don't quite have the capability to model on our system, at least not now. So the first one that I want to show is the Antelope Creek. It's a small tributary of the Red in North Dakota. And Mike DeWeese from the office here prepared this graph. You can see that the relationship between the snow water equivalent and the runoff coefficient is pretty well aligned along the straight line. The last few years, the higher ones, 2011, 2010, 2009, are here, but look at where 2013 is. We would have expected 2013 to be around here, near 100% runoff, which is essentially what our model was telling us. But the runoff coefficient, at least in Antelope Creek, was about roughly 20%. The big question is, where did the water go? Trying to answer the question, I looked at the degree day charts for Fargo, and I prepared those based on an average daily temperature computed with a simple average of the maximum and minimum temperature for every day. And we see that for 1989, the temperature started to rise faster than in 2013. By the way, those curves start with the onset of the high rise on each one of the seasons. And we see that for the daily temperature, there is kind of below freezing. This is those degrees above freezing, so it is in Fahrenheit, but in degrees above freezing. We look at the maximum daily temperature, and we see that that the 1989 curve was slightly higher than the 2013, up until about the first 6 days of melting. But that's about how much time it takes to melt. But the big difference was here. While in 1989, the minimum temperature stayed just roughly around freezing, in 2013, it was considerably colder. So we have the case that there was some melt during the day and freezing at night. So the question is, where did the water go? If we compare both cases, 1989 and 2013 were both preceded by drought. And in fact, the drought in 1989 was more severe than in 2013. The snow water equivalent during 1989 was roughly one half of that of 2013. In some places, a little bit less than half, in some places more than half, but just roughly one half. The peak flow in 1989 was higher than the one in 2013. While with a smaller amount of snow water equivalent, that can be explained by the faster rate of snow melt that will cause a faster peak. But the big puzzle is what happened to the volume of water in 2013. So we started to look at the soil. Professor David Hopkins from NDSU sent us a photo by John Nowatzki south of the Red River Valley Fairgrounds. And just to give an idea of the scale, I have a marker showing the size of the cracks that develop on the Red River Valley during a drought. You can basically drive a truck through that. Another important one is this video that we got from Al Volker, who was visiting a friend near Grand Forks. He's one of the meteorologists at the Grand Forks office. And by the way, you should correct in the handouts. I didn't have his name yet, but I got his name this morning. And let me play this video for you. It's very short, but it's very, very telling. It is very difficult to explain how the rate of infiltration that we see on clay soil, unless there are major cracks that have been developed that will provide the volume of water that is replacing the bubbles of air that are coming to the surface. For a second. Okay. We also got this Red River soil profile from Professor Hopkins, and one of the things I wanted to show is that this organic, what do you call that, columns of material that definitely provide a higher infiltration rate than the one that will be obtained from a clay soil. But we also see this prismatic column that can form on the horizontal structures. I should point out that it is very difficult or essentially possible for our lumped model to be able to consider those variability, the variability of the soil, the spatial variability of the soil with the lumped model. But even so, the model just doesn't assume that you can have clay soil which is almost impervious, and all of a sudden you can have soil that is so pervious that it looks more like a gravel pit. Another problem that appears on the Red River is the tile drains. It's called tile just simply because of historical reasons, but they're now plastic pipes. And you can appreciate the magnitude of this pipe. It's about at least 14, maybe 16 inches in diameter. And For you to have an idea of what an impact these are making, I wanted to see this question: how many miles of tethering have been installed on the Boilersu River, which is only 5.2% of the Red River above Pembina? To give a comparison, the city of Fargo has 528 miles of city streets, and Grand Forks has about 240 miles. The amount of miles, or the number of miles that have been up until December of this past year is about 10,000 miles. And if you see, the growth is exponential, with an R-square of 0.9946. Of course, it cannot be exponential forever because there's a limited amount of land and limited number of farms that can be drained. But the big question for us is, how is this, and especially this changing in time, affecting our ability to do forecasts when we are doing the calibration with historical data that didn't have that type of information available? Another factor is this, and this is a flight taken at the end of April of this year. And I wanted to point out the following. If you look at the image, you see that these fields here are flooded right up to the road embankment. Immediately past the embankment, the soils are dry. At least there's no standing water in them. This is particularly clear here. The question that comes up is why? Are there culverts that are frozen? Are there culverts that are controlled by farmers? We just don't have the answer to that. But clearly when you have standing water, the hydraulic head that is pressing on the soil will have increasing rates of infiltration than the ones that were just simply from surface runoff. Here's this little cartoon to try to illustrate one of the hypotheses that we are working on. And we have a case of Fargo clay. And if we have drought, the drought will create cracks between soil columns. Okay? And if on top of that we have freeze, which is the frozen soil, and snow on top of that, and we have some of the snow and ice just getting into the cracks. This is to try to explain the differences in the runoff between 1989 and 2013. In 1989, we have a fairly rapid snowmelt, as I showed by the more rapidly warming up of the snowpack, and a smaller snowpack that allowed it to melt faster. But because of the faster melt, it didn't allow the soil to thaw as fast. Therefore, it probably kept some plugs of ice still in the cracks, protected by the cold soil, that maintained the soil to be essentially impervious. In contrast, in 2013, the very slow and prolonged snowmelt allowed the soil to be melted from underneath. The snowpack also served as a insulator to prevent it from freezing anymore. And that once the plugs disappear, it allowed water to infiltrate. And that may explain why the water going into deep groundwater, not onto shallow groundwater, was never out in the river. So if we have a runoff coefficient of about 20% compared to nearly 100% that was observed in 1989, that may be a mechanism, but I just don't know whether the mechanism is right or not. What we would like to do is to get the right result for the right reasons. I mean, I don't want to be like the Ptolemeus and Copernicus that the theory that explained the movement of the planets around the sun was perfectly wrong, even though they were able to predict the position of the planets perfectly well. What I would like to do is to predict the flows on the Red River the best possible way, but for the right reasons. So what are my conclusions? My conclusions are that the frequency of flows at all ranges on the Red River of Fargo is increasing, and Skip's presentation will talk about that. And what are the possible causes for the overall flow increase? If we compare the 1989 and the 2013 flows, we see that the flows were relatively similar, with a little bit higher in 1989. The 1989 snow water equivalent was about half of the 2013. And in 1989, the volume at the peak of flow were very accurately simulated. In 2013, the volume and the peak flow was considerably overestimated. But why? What are the causes? Is that the sequence of drought, freeze, and melt on the Red River. Do the tidal rains have an impact on the most recent performance of the Red River? Factor of the abundant and undrained fields. The changes on the land use, maybe the crops, and Skip will talk about that next. What about the effect of levee construction? Those are questions that we would like to ask you if you have any suggestions for us to consider, and we will very much appreciate that. And thank you very much, and let's start with Skip presentation. Skip, do you want me to give you control?
Yeah, we can try that.
Okay, which viewer are you? I don't see you by name.
Well, I didn't have to sign in by name.
Okay. Well, in that case, let me give you the presentation here, and then you can tell me where to to start. Okay.
All right.
Well, when to change.
What's the matter, Ollie?
Hello.
Pedro, while you do that, could you tell me how far ahead you make the forecast compared with the measurements?
Forecast. Red. The lead time one?
Yeah, the lead time, yes.
This is Andrea. We try and do the deterministic forecast about a week before the melt begins, and we do the probabilistic forecast starting in January.
Okay. So when the melt starts, you have like 30 days or so before the peak, and you forecasted the peak very well. Or is that a good assessment of what I'm saying?
When? This year? No.
What forecast was that?
Oh, when we do forecast, yeah, that was about 10 days ahead of time. And also for the red, the driver by far is temperature. And temperature forecasts, especially this year, were particularly accurate.
Okay.
Okay.
Pedro, this is Jeff. Can you check that you've got your computer on full screen? It's not filling up our screen.
It's as clear as it will get, Jeff.
Thank you.
You're welcome. Or as they say here, you betcha.
Okay. Can everybody hear me okay, I assume? And I'll get started. I'm Skip Vecchia with the North Dakota Water Science Center of the USGS. And I'm going to talk about this increase in flood risk that Pedro mentioned for the red, but it's really a regional phenomenon that's occurring, and whether that seems to be maybe climate related or land use related or both. Okay, next slide. So the study I'm going to talk about covers a 9-state area shown here, and there are 25 USGS stream gauges we used, indicated by the basins here, and we split them into 4 regions, A, B, C, and D, extending from Minnesota down into southern Missouri, eastern Kansas. So with this presentation, I want to describe some of the complex historical patterns we've seen in climate and runoff in this study area. Okay, next slide. This is a paper by Hirsch and Ryberg, and they looked at changes in annual flood peaks for 200 long-term stream gauges. And what you see is for that 9-state region circled there, this is the bullseye for the largest and most significant increases in flood peaks in the 20th century. They also showed that using bootstrapping that this was not related to global warming or climate change, if you want, per se. And others in the Weather Service, I think, have shown the same thing, and I've been involved with a couple of papers with similar conclusions that this phenomenon is not really a global warming issue. It's more a climate variability issue. Okay, next slide.
Yeah, 1 second, Skip. Jeff, or all the viewers, if you see in the center of your screen a magnifying glass with a plus sign, if you click on it, it will give you the full. It will fit to the screen. We'll maximize it.
Thank you. I do have one question about that last slide. Was that from the pristine USGS network, or was that from the general network, what you've got plotted here?
There are 200 gauges that were the least affected by development. They're not really pristine, but they're as close as we could get.
Thank you.
Okay, so the working hypothesis that we went with was that there are transient changes between wet-dry conditions on decadal and higher time scales. The changes are very complex in terms of, seasons and regional coverage. That changes in precipitation amounts and patterns during these periods could explain a lot of the variability we're seeing in floods, and that the effects of land use or other changes, although they may be there and may be important, are small in relation to precipitation. And equivalently, if they're small, it means they're going to be hard to detect or hard to separate. But we did try to separate the two effects. Okay, next slide. So the details are in this recent paper in Journal of Hydrologic Engineering, so I won't really give any details of the modeling. This is by Ryberg, Wei-Lin, and myself. So if you're interested, you can look at that. Next slide. Okay, we wanted to look at not just runoff and separately. We wanted to look at the water balance. So of course we needed precip temperature and potential ET data. For that, we relied on the historical climatology network, and the stations here for the 9-state region are shown. So we did our own method of interpolating this data to a regular grid over the area. After the fact, we went back and used PRISM data and ended up, we would have gotten the same conclusions, but we wanted to be sure that we weren't getting anything in our data that was some artifact of the way the data was computed. So this, now I want to talk about this, what I mentioned of these sort of transitions between wet and dry periods through time. So if we look at that 9-state area and look at precipitation, this shows we decided to use 2 seasons, January through June, which is on top, and could call that the cool season, and July through December on the bottom. So that would be the warm season precipitation. It's described in the paper why we chose these 2 seasons. And we also chose, whoops, did you go back? We also decided to look at, a 12-year time interval. Again, that's mentioned why we did that in the paper. We wanted to look at, sort of smooth out the year-to-year variability, but still keep some of this longer-term variability. So the red line here just shows the percent of that region that's in wet conditions, and the blue line shows the percent that's in dry. And this time series extends from 1900 to 2010. So you can see clearly the 30s drought, with very much of the area in dry conditions, particularly in the July through December season. There was a wet period in the mid-40s that was during January through June. There was another drought in the 50s that covered mainly the southern part of the region. You can see this very long period in July through December of wet conditions starting in about the 1970s, and we're all probably pretty familiar with that phenomenon, much wetter fall conditions. So what we did for the water balance analysis, we defined 6 of these periods shown here in gray because we wanted separate periods, and we did a water balance for each of those separate periods, and we wanted to compare them and see what sort of changes we could find. Okay, next slide. This just reminds you of the 4 regions and 25 stream gauges. Next slide. Okay, before I get to the water balance, I have a couple slides, and the purpose for these slides is really twofold. One is to show that the runoff volumes are behaving very similarly to flood peaks. And the other is to show that why it is so much harder to model stream flow in Region B, which includes part of the red, than other areas. So this is Region D. Well, go back to Region D, previous slide. For Region D down in Missouri, you can see in that January through June, so this is precipitation in the left panels, or the top ones, and runoff in the bottom. And on the left is January through June, the right is July through December. So what you see is for this area, for one, the 7-day high flow, which is in orange, behaves, these are dimensionless, so each station was divided by its mean and then they were averaged to get sort of an overall pattern, so they could all plot on the same scale. So this shows that the floods are behaving very similarly to runoff volumes. And also you can see how closely in both seasons the precip and runoff patterns correspond. So if we were just looking at this region, there wouldn't be much to do. I think and we did in fact find there was no evidence of anything affecting runoff besides these precipitation patterns that coincided very closely. Now go to the next slide. Let's contrast that with Region B, which includes the red. What you start to see is basin, first of all, we get a lot less precipitation. In Region D, there was about 20 inches in both seasons. We get about 11. In Region D, there was about 8 and 4 inches of runoff. Well, in Region B, we get 1.5 inches in January through June, long-term average, 0.7 inches in July through December. So we're trying to track a very small amount of runoff compared to the wetter regions. Another thing you see is if you look at the left-hand side, the January through June, if you look at the recent runoff, it's much higher than it was in the mid-40s, and yet precipitation, the top one, was very similar in the mid-40s to recently. And through the water balance analysis, we determined that that was mostly caused by an interaction between the July through December season and January through June. In other words, the wet conditions that we're seeing in the fall were carrying over into January through June. Okay, so we've got that issue. And also, if you look at the right-hand panel, July through December, we've got huge variability compared to the other region. For example, precip, if you look at that point in the mid-90s, we're averaging about 1.5 inches more precip, and you go to the bottom one, we're averaging about 1.1 inches more runoff than the long-term average. Well, compared to 0.7 inches, that's 220%. So a little bit more precipitation can really, in terms percentage-wise, 15% more precipitation produce more than 100% increase in volume. Okay, next slide. Now I'll get back to the water balance, and what I'll kind of hit on a couple things that I think are relevant for today, the purpose of forecasting models, maybe help us point us in the right direction, maybe to be looking. We were able to come up with a nonlinear water balance model, a very simple model that basically just had 2 parameters in it. And for those 6 12-year intervals in the 19 basins in 3 groups, and we actually threw out Group A because it was behaving very differently than these. Had a very different water balance. It's more forested. These are more ag areas. But for the 3 groups, based on that simple water balance model, on the right-hand side here is shown the fitted runoff versus the observed. And you can see that that simple model explained 97% of the variability in Season 1, 94% in Season 2. So right away, you see that we're not left with a lot. We're left with about 3% in Season 1 and 6% in Season 2 that we can attribute to something like land use or something else. So it just indicates how dominant precipitation the climate variables are. The left-hand side, just I put that in to show that basically the water balance, all we're doing is trying to estimate how much actual ET there was. So on the bottom axis, this is precipitation, and you can see runoff, and the top line is runoff plus estimated ET. So if we could get ET perfectly, that line would be 1-to-1. Well, it's not 1-to-1, but it's pretty darn good. So it shows that the water balance model is doing a good job of estimating the actual ET that's taking place. So I could stop here and say climate, these shifts in precip are causing most of the variability, but we did want to go beyond that because for a forecast model, some of these other issues could be very important. So if we look at the residuals from this model, so we take out the climate effects and see what's left. And what was interesting is that when we did that, if you can analyze these statistically to see if there's any difference between those 6 periods. And for group D, as I already mentioned, there was no significant difference. So climate was pretty much everything. But for groups B and C, which are heavily agricultural, row cropped, there was a highly significant increase in runoff from the 50s to the 80s, or equivalently a decrease in ET. Now, it's not very large. It's only about a total of 20 millimeters. But you can see it's very similar and very consistent. This period was during a time where there was a lot of land put into row crops, corn and soybeans. So you might expect it to increase ET. So one possibility would be that drainage, maybe there was also drainage occurring at this time that was able to compensate, particularly since this is during the January through June season. Perhaps there was drainage that more than compensated for that and resulted in more runoff. So this is just sort of an aggregate of all the land use effects. You really have to get more deeper to actually see, well, which one is it? But it's kind of counterintuitive. The other thing I wanted to show, and this, Pedro looked at 2013, which is outside of this. But when we look at the most recent period we analyzed, 98 to 2009, we didn't see any difference at all with the 1982 to 93 period. So this would indicate that more recent land use changes are not really having a discernible effect on the water balance compared to the earlier changes. And I was going to say that things like tile drainage might be in there, but then I saw the slide Pedro put up for that one, and the tile drainage started going crazy after 2010. So this only goes through 2009. So this doesn't say very recent tile drainage isn't having an effect. It's just saying that whatever happened since 93, land use-wise, apparently has not really affected our runoff very much. Okay, and last slide. So in conclusion, these upward trends in flooding that we're seeing are can be attributed to precipitation patterns, but they're sort of transient and chaotic patterns. They are clearly related to ocean temperature and atmospheric circulation, but really very difficult to predict. But these shifts occur and persist for long periods of time, like we've seen for these wet fall conditions, for example. We were able to show that about 80% of the recent increase in flood risk for regions B and C were due to the precipitation and about 20% to land use. So even though precipitation dominated, there was part of the increase that, particularly during that 50s through the 80s, that could be contributed to land use. I've already mentioned recent land use changes don't seem to be making a difference. And the trend we're seeing, land use effects, whatever they are, whether it be drainage or change in cropping, whatever the land use changes are, seem to have resulted in lower ET or equivalently more runoff rather than the reverse. And finally, where does this come in for real-time forecasting? Well, this is more almost a cartoon when you get down to that level. But I think it does give us some idea that maybe if we want to improve the forecasting models, the place we should look is at these processes like Pedro was talking about, the frozen soils, the timing of the melt, some of these processes that can affect the runoff rather than, say, maybe land use changes or something like that. So that's everything I had. Thank you, Pedro, for putting those up, and I'll send it back to Pedro for questions on his talk and mine.
Thank you very much, Skip. And so let me open the lines here for questions or comments. All are welcome.
Hey, Pedro, this is Lori from Eastern Region. I'll jump in very quickly because...
Lori.
Good afternoon. I grew up in the Red River Valley, and my father's farm was a mile and a half from the headwaters of Boise Sioux. And so Skip slides that talk about the land use changes of the 50s to the 1980s. My father was a township clerk, and he kept minutes of authorization of who was going to be draining what little pothole in some field out into the township ditches. And I can tell you, he would swear and cuss because his fields were the closest ones to the river, and he got all the water from everybody else. So during that era, there really was a very significant change in farmer and drainage practices for those, at least I know of, in the southern tier of the Red River Valley, Richland County. The other thing that I can tell you is by about into the 80s, probably those types of requests didn't happen anymore because they had done everything they could already to drain out the water off their fields that were further away from the river. Okay, so what Skip was showing in his slides makes sense to me from my anecdotal experience of having lived there. And also, I still own farmland there, and this ramp up of tiling going into different fields around the area, I do think that will have an impact on the river modeling. Hard to say what it will or won't be, because, the peak runoff is when the ground's still frozen, generally speaking. But I found Skip's presentation very interesting. And one other thing that might explain something in your analysis, Skip, is my father had also talked about the Corps of Engineers dredging the river in like the late 30s or possibly into the early 40s. And prior to that, there had been no sort of dike or levee on any of the river banks there. And so that all came about in that era.
Thanks, Lori.
Thank you very much for that.
Mm-hmm.
Any other questions, comments?
This is Jeff here. Lori, when you talked about change in farming practices, what sort of changes are you referring to?
The farmers would drain out sloughs and potholes, and they would make larger culverts would get installed, things like that would take the water away from the fields more quickly, so they'd have a drier field so they could get out more quickly in the springtime, get their, the digging, the plowing, the seeds planted, all that type of thing. There's a pressure to do that, get your growing season underway, and so you can reap the spring moisture, grow different crops that have longer growing seasons, get better prices, things like that. And that was the era, especially in the 80s, where a huge change, interest rates, things like that going on, at least as I remember as a child or young adult.
Thank you. I do have another question for Skip. Skip, in your analysis, you broke it up into those two seasons, and the first one was January through June. January through June, I believe. And I'm wondering what your analysis would look like if you made that window smaller and coincided with the chart, the graph that Pedro showed of when the peaks occurred in the year, and you kind of focused just on that window.
That's a good question. We did look at starting with actually 4 seasons. Karen in our office was doing a lot of this work too, but we sort of decided it was getting so complicated that the two seasons kind of told a lot of the story. But I do think we could find, if we did go to more seasons, we could probably do some more analysis in that respect.
I think with such a broad season there, December through June, you're covering a fairly broad range of frozen through unfrozen period, and it seems to be that the transitions occur fairly narrowly, and so you might be averaging out a whole bunch of things. And then I thought what Laura said about trying to get into the fields earlier and doing that drainage, they seem to be focused on that rapid tipping point. It's not the right word to use, but that rapid period of thought. Go ahead.
Yeah, I mean, it would tend to be a rapid type of, you go from waiting, and then bam, you had a ton of work to do, incredible amount of work to do. So really there was always a great anticipation for trying to spread that huge initial workload in the spring out a little bit longer. So the sooner you could get in, the shorter days you had,
Well, Pedro, could you go to the next slide, Region D?
Sure.
Region D, I think, shows clearly there's none of this, what you're talking about, but I think...
I'm sorry, region?
That slide. I think some of the things you're talking about would show up when you look at the 7-day high flow versus the mean, because that gets more at timing issues. So there are some deviations here, and that may be one way to explain those is through these other sorts of processes. And so particularly in the January through June, when we get our peak flows, there's not perfect correspondence. So there are other things going on in that you're talking about, but the overall volume seems to be a large part of it.
This is John. I'd like to follow up on Skip's thoughts there. I was having some similar ones. I was just wondering if you were to analyze the simulations from the Weather Service model of places in the Red River, like you analyzed the historical data, the observed data, and I'm curious whether the model behaves like the observed data if you were to do a very similar analysis to what you did. You used your nonlinear model to get some insights here, but you have actually daily data from the Weather Service simulations. I just wonder if they're behaving like the real world in a way that follows some of these other patterns. It might get some insights where they deviate.
That's good. Is Steve Buin on, or Andrea, I guess, is on? That would be kind of neat to compare. I mean, if we could get, in particular, at how much ET the Weather Service is estimating in these seasons, we could compare it to what we're getting. That would be interesting.
Yes, Skip, we can start those simulations in 1968, so we can certainly do that for comparison.
Yeah, and we would definitely be interested in that, especially could do it for more individual basins in the red rather than this regional thing.
And Pedro, the runs you guys have made is not the HT-ET version of SAC, is it?
Correct. It's the old version.
And by old, you mean straight SAC or SAC HT?
No, it is a straight SAC with the old frozen ground component. But it's not the SAC HT-AT, the lump model.
Hi, Pedro.
Hello.
Hi, this is Xinhua Jia from NDSU.
Hi, Xinhua.
Hi. We have 280 covariance weather stations that running all the time for the ET measurement. It's for the actual ET measurement. So, if there's any need for that, we can definitely step in.
Thank you very much, and we really appreciate all the information that you send us to on the soil temperatures and snow water equivalent and so on. Thank you, Xinhua. As you know, because the observations in North Dakota are so sparse, anything that we can get is particularly prized by us.
Yeah. Okay. Yep.
Hey, Pedro, this is Mike Smith.
Sorry, who's this?
This is Mike Smith in OHD.
Hey, Mike.
I'd like to get back to your question of where did the water go?
Yep.
So can you hear me okay?
Yes, we can hear you fine.
Okay, so in 2013 you had a large oversimulation, and then, so did you, in the observed data, did you ever see any rise in the river during the summer? Did the balance eventually, or did the simulation and the observed eventually balance out? Because if you looked at the whole water year, you might see the volume coming out slower.
No, we don't see it, Mike. My assumption is that water is going to deep groundwater, maybe coming out in 100 years or so. I mean, the area is so flat that the gradient for the groundwater is very low, and any water going down into the deep groundwater is not going to be seen for a while. Well, we haven't seen it, to answer your question.
Okay, so it's going somewhere. So if it's moving into the soil, if it's moving into the soil at a rapid rate because of these large cracks that never close up because they're frozen, then maybe it'd be interesting to look at the local groundwater levels to see if there's a rise. I think I looked at a few of those over there.
Right.
And not only do they rise, because they probably all will, but is there an unusually rapid rise due to the cracks?
Yeah, we do see that. I mean, some of the graphics that you sent us, there's some very rapid rise.
Yeah,
so I think it's an area that is definitely deserves a much more detailed look.
Right. Yeah, and I don't know what qualifies as a rapid rise versus a normal rise. If you had this drought in those 2 seasons that created large cracks, and that led to a rapid rise, somebody else with more smarts would have to figure out if that's a rapid rise. And then if it does go into those groundwater tables, then it never really appears in the stream flow, right? It has to go somewhere, or else, like you said, maybe it does appear in the stream flow, but over much longer period at a much slower rate. So in a sense, you really don't see it in your water balance.
Right, and one thing that would be very interesting to do for the GS, I guess, or for some of the universities, is to do an isotope analysis and see what the age of the water is.
Right. And then it'd be very interesting to see how deep these cracks go and how prevalent they are throughout the Red River. Is it just in isolated areas, or is it really a widespread phenomenon?
Well, if you ask me, they would probably go all the way down to China.
Okay. And then another comment was more on what happens when you put tile drains in. And I understand the purpose of tile drains is to get the water out of the soil so you have the optimum conditions for growing crops. And I think the second presenter said that there was a rapid transition into agricultural land in the mid-'80s or sometime. And what was the land before that? What was the land use? Like if it went to alfalfa and hay or whatever, what was it before that?
Skip?
No. I guess I could. This is Lori. I could talk to that.
Okay, sure.
Yeah. In the late '60s, there were still farmers that raised something like alfalfa and hay in the Red River Valley, and they had feedlots and things like that. With the commodity prices that rose significantly in the late '70s, '80s, all that land that, you used to go out and bale hay and things like that. That was all put into soybeans. If you could grow corn, you did. It went into sugar beets.
Okay.
Sunflowers, that type of thing.
Yeah, and this was Skip. There were probably millions of acres of wheat converted to corn and soybeans also during that time.
Okay.
So.
This is Mark Goodner in Fargo.
Hey, Mark.
The change in farming practices, I think, have a significant impact on. I know I was raised on a farm, and our crop rotation was a 3-year rotation, and so a third of it was summer fallow, and we did have cattle, and so we did have some alfalfa, and then so the additional acreage for cropland. Partly associated with the elimination of that third year rotation, and they went to intensive farming. Having said that, it seems to me that with a coverless field would freeze deeper. You didn't have any cover crop on it. Would freeze deeper and would increase the runoff.
Yeah, this is Laura. I would agree with that. And sometimes people left it stubble, and sometimes they didn't.
And the other thing that I think I would agree with the statement that most of the drainage occurred, a large percentage of the drainage occurred in that period of 50s to the 80s, particularly on the Minnesota side, whereas in North Dakota there's still some growth in drainage can be anticipated because it's not totally drained as well as the land in the Minnesota side.
Mark.
Yes.
I was wondering if you could send us as much information as you have about all of those factors that are on the soil: temperatures, frost depth, sort of snow water equivalent. That will really help us come up with a much better forecast this year.
Yeah, certainly we can assist you on whatever information we have.
I think, and the other question that I had is, why are those fields still flooded? I mean, the water is not draining to the next field. You see the lower part of the field wet, and the next field, the higher part, dry, and it should be going downstream, but it seems to be stopped by the embankments. Do you have any idea why? Are the culverts frozen, or are there any type of gates that control the flow of water under the embankments?
This is Chad from Moore Engineering. I'm engineer for a lot of the water resource districts in the Red River Valley on the North Dakota side. There's very few gates on road culverts. I mean, the percent would be less than 1%. That's not, there's no formal plan or anything like that with gates and operating at roads. So that's not it. One thing I would caution you on is when you're looking at aerials and you see one side of the road, water is ponded, and then on the downstream side, or the side that's lower in elevation, it's dry, there's not always culverts connecting them. And a lot of times the culverts aren't taking the flow in the direction that you would think it would intuitively. They might be taking it laterally instead of immediately down gradient, if you follow me.
Yes, I do follow you.
Okay, yeah, so that's very common in the Red River Valley because it's so flat that water doesn't always flow with the gradient of the land. It's because the ditch systems can be graded deeper than the landscape and cause the water to flow in a direction that you wouldn't anticipate when you look at the overall topography. The culverts being frozen, that can happen, but I looked at your pictures, and those pictures that you had on the presentation today look to be a little bit more in the later stages of the flood. Generally, you see culverts froze when there's still snow on the ground, for example, snow and ice, and your pictures appeared to be a little bit later in the flood. I didn't see any ice or snow in the landscape.
There were snow. The pictures actually were on the last day of February, if I remember it correctly. I still have the date exactly. So it was before the peak, and there were still down some places, not totally covered everywhere, but there was still some snow on the ground in those pictures.
Yeah, but culvert freezing is a phenomenon. It can happen. It's more typical right in the very beginning of a flood event, however. So there's a lot going on out there, I know, with how water is getting ponded, and each area has its own special explanations for why you see what you see from an airplane.
Well, thanks, Chad. The reduction in increase in runoff in later periods here is possibly related to sodbuster, or what's the water?
Yeah, swamp buster.
Swamp busters legislation that started to require some permits for drainage.
Yeah, when you look back, at least in our files, we have record drawings of most of the drains that were constructed in Cass County and adjacent areas anyway. And that you see a lot of SCS. SCS was big into assisting drainage back in the day, and a lot of their plans are dated in the 50s and 60s and 70s. It's real common. They had funding for that. And then when Swamp Buster came along, that definitely slowed the pace of at least new public-type drainage. Granted, there's probably smaller private drainage going on and things like that, but once Swamp Buster came out, I think that really slowed the pace of it down, and that's why I think your trend ended in the 80s.
I think the flooding that we're seeing is certainly related to the amount of precip. I've seen a chart similar to these as part of our overall flood protection strategy, where NSU came up with a 7-year rolling average of precip, and that really showed on an annual basis how we're really into the wet cycle now.
This is Aaron Busing with the St. Paul District Corps. As far as the photos showing the ponding, and that's pretty common with all the floods, at least all the recent floods. So I don't know, maybe in combination with the drought, the ponding increases infiltration some, but I wouldn't think that'd be a major factor. I guess.
Right, because it's the same.
What are you guys?
Yeah.
Right. I guess what methods are being looked at as far as measuring soil temperature and infiltration better than what we're doing now?
Well, we don't have any. Just that we have to rely on a few volunteers, like Professor Xinhua Yang at NDSU, and some North Dakota and Minnesota observations, but they are very sparse and very few in between.
This is Jeff here. It seems to me from the discussion that what I'm interpreting from the discussion is that issues associated with frozen culverts and things like that are more likely to have an effect on the timing of the movement of the water into the river. Whereas, coming back to Mike's point, where did the water go? What we seem to be looking at as the essential problem that you're trying to address, Pedro, is that the water just is disappearing. It's not an issue of timing over a month or two or something like that. So it seems to me that unless we can say that there's something about culverts and tile drains that delivers it to the deep aquifer, then it's probably worth not thinking about that issue all that much and trying to focus on other issues.
My problem, of course, Jeff, is the fact that the overforecast cost the city of Fargo and the Corps of Engineers a lot of money. And, of course, it is better to overforecast than to underforecast, but the idea would be, of course, to do it the right way. And if we have similar situations like the one on the red today, I mean, in 2013, well, we will have already an analog that will guide us. The problem that we had was there was no analog for this very late and very slow snowmelt, and we were just guided by what the model was telling us. And clearly, the model is just not representing the what is happening on the red. So, no data to validate. Yeah, and the lack of data to validate, just the lack of data to validate what is the moisture, what is the temperature of the soil, what is the depth freeze, and how is it melting, and so on. So that's our.
Perhaps I didn't make my point sufficiently clear. So I understand what your concern is from the user's point of view, but it seems to me from the point of view of trying to analyze the physics of what's going on, it's less likely to be frozen culverts and things that would move the timing of the water by months. It's more likely to be something that provides the water down to the deep aquifer that just gets rid of it, because you've clearly said that you don't see the water later in the season.
Right. Well, I agree 100% with you.
Okay.
I agree with that. I think that that one chart showed the nighttime temperatures, which extended the thaw, which and that water was ponded because it wasn't getting warm enough to break open the drainage system. I think a lot more did.
Hey, Mark?
Yeah.
Hello, Mark? Yeah, we lost you for a second.
Can you hear us now?
Yes, we can.
Okay.
Yeah, I think that one temperature chart you showed of the evening temperatures where it cooled beyond freezing is a very telling picture for me, in that during the day you would melt, but it wasn't enough to open up the drainage systems, or totally open up. So I think the water sitting on the fields did infiltrate a lot more and did go, it disappeared into some places.
I think, Mark, that we could do is maybe to coordinate with you and your people in your office for the next flooding season, for you guys to give us some additional observations of the frozen ground depth and also the status of those culverts, for us to start to understand what the process of the Red River is.
Pedro?
I go back to 1997 when Fargo and Grand Forks peaked about the same time. In Fargo, we had the mayor flying up and looking and counting sections of land that were underwater, and he said there was 50 to 60 sections every day that were underwater. And we're still underwater when we crested. And the day after Grand Forks went under, flew over Grand Forks and saw that there wasn't any upstream land underwater. So I think that ponding does significantly reduce we have a natural waterfall effect upstream of Fargo, or Grand Forks doesn't.
Yeah, and that's a peak and timing issue, and not related to the other point about volume. The water simply just
Right.
This is Skip. Guys, can I just say one thing on the volume thing? I disagree that it's disappearing to deep aquifers. I believe that the water where it went was to replenish soil moisture deficits from 2012. So maybe the problem was that there was more deficit than was estimated by the model. So maybe getting those deficits. Anyway, and then Greg has a question for Pedro. Greg Wiki.
Okay. I guess, I've heard a lot of good discussion, 1989, how that might have happened versus 2013. And I agree, I agree with almost everything I've heard so far on what we might focus and look at. The one, I think, more problematic, I'd like to hear some discussion on, you showed 2009, the second peak, when in fact we should have met infiltration. I mean, I think that one warrants some discussion as well.
Okay, let me put Mike to talk about that one.
Hey, Greg, this is Mike DeWeese here at the River Center. I agree with you, and we haven't really touched on 2009, but Mike Smith kind of was discussing that earlier, this issue of losing volume. The 2009 event, on that second crest, we did lose the volume, but we also saw some really prolonged high flows in the river where the volume came out later. What we didn't see in 2013 was the volume show up. So it clearly went into storage, whether groundwater or deep soil moisture. But the main thing, from my experience, the difference between those two events that I see is the rate of the melt that occurred. We had one site in Wilkin County, I think, Minnesota Department of Ag site, where we actually had soil temperatures throughout the whole profile. And what we saw this year was really unusual because as the soil started to thaw, when we hit that prolonged cool spell, that process basically just stalled out for about 2 weeks. Mm-hmm. The soil temperatures, I think, were the big difference. The way the thaw developed this year versus 2009. 2009 was more of a traditional melt where it occurs a little faster in a more compressed time frame. My hypothesis this year is we had such a slow, prolonged melt at the surface, and we had that long, prolonged period where the soils were just kind of on the threshold of melting, that we can't really tell because we have no data to substantiate that. But that may be why we saw such a higher rate of infiltration this year, combined with the dry soils, as opposed to 2009.
Yeah, well, like I say, the hypothesis we have for this year, I can pretty well live with. But 2009, the way, as wet as it was, to have that disappear on that second peak is much more puzzling to me.
Yeah, 2009 was more complex, I think. But we also are confident that we had that volume in the snowpack. So the question remains, where did it go?
This is Tim. Hi, this is Tim Zaliga from No Risk. I want to concur with what Mike was saying. I'm not a hydrologist, so I feel free to oversimplify things. And we got a lot of lucky weather. There were several heavy rainstorms that manifested themselves as snowstorms. Our charts are just measuring the precip, but a lot of them came down as heavy snowfall, and that gave a time delay that allowed things to move a little more slowly than if a just downpour would have happened, and that could have melted the rain on the snow.
Tim, is that 2009?
Yeah, this was 13. My memory doesn't go back to 2009.
Well, 2009 was primarily, the first crest was primarily the Red Basin, and the second predicted crest was more of the Cheyenne River coming from the North Dakota side. And that was delayed by the weather that was earlier described. And the volume was there, just that it came later.
Pedro, have you guys looked at the winds for 2013 and seen if there was a huge increase in evaporation or sublimation?
Hold on a second. There was no. Let me give my answer first, and then I'll put Andrea. My guess is that there was not a huge increase in evaporation because the temperatures were so cold anyway. And
yeah, but the solar insolation really increases.
No, it was pretty overcast. For what I remember, it wasn't.
Okay.
Hey, Andrea.
Hello?
Hi, this is Andrea. There was more sublimation in 2013 than is normal, than is typical, like a whole month's worth more. But the highest sublimation rates that we were seeing was like 1 millimeter per day. It wasn't a whole lot. We couldn't use that to simply explain the loss of the water. There had to have been more than just sublimation.
Thanks, Andrea.
So this is Paul Barlow in Massachusetts. I was wondering, when you look at stream flow, have you looked at any changes in the possible contributions to stream flow in terms of base flow versus runoff for these areas?
Paul, say again.
Have you looked, you can do like base flow separation analyses and look at the source of water to stream flow. Have you done any of those kind of analyses for this area?
For the particular year of the 2013?
Well, just over time. The reason I mention it is we do a fair number of base flow analyses here, and while we were talking here, I just randomly selected a couple of gauges out there, and I don't know anything about the basin, but there seem to be some changes over time at these sites that I'm looking at in the percentage, basically, of groundwater discharge to these streams. So I'm just kind of wondering if you looked at that.
No, we have not looked at that, but it's a good point because with increasing in tile drains, that may explain some of the changes that you observed.
Yeah. Well, Skip, maybe you and I could talk about that after the call here.
Yeah, I'd be interested in talking about that.
Pedro, this is Mike Smith again. I wonder with the, all the increase in the tile drains, which are put in place to take moisture out of the soil so that you have the optimum growing conditions for the plants, that you're removing the soil moisture that would really evaporate or evapotranspirate, and you're putting it into a tile and eventually into a stream. So I wonder if they're somehow responsible for the reduced ET rates that we're seeing.
Can I say something about ET?
Sure.
Okay. Well, we all know that with tile drainage, your crop yield increase. If your crop yield increase, your ET is increased. So forget about the moisture, just think about the yield. So it's not, during the growing season, the ET is not decreased, it's increased because the healthy plant, the deep-rooted plants, the evaporation from the wet or dry surface between drained and undrained is a very short frame, time frame in the early springtime. So for the entire season, it's an increased ET for tile drain field.
Okay, thank you.
I got a comment for Skip and Pedro. Can you hear me?
Yes.
This is Dan Reinertz. I'm with the DNR. But for the 2009 event, I was a fusion cell for the Corps embedded in with the National Weather Service. I missed the first part of this presentation, and maybe you covered it, but I'll present to you my impressions of that 2009 event. I recall that the forecast was very close on the first peak, but then we had that freezing cold weather that came in that froze the runoff. And what I recall in that intervening period, just before the runoff resumed, there was this ponded area upstream of Fargo in the vicinity of the Wild Rice River. And there was another ponded area down by Hallstatt that you could see in the aerial photos. So one day, that ponded water was there. The next day, the ponded water was gone. And my impression was that was right at the time when the frost went out and infiltration began. So I attributed that ponded water as soaking right into the ground for that region just upstream of Fargo in the vicinity of the Wild Rice River. You could probably calculate what that infiltration rate is, but I would caution you not to use the saturated hydraulic conductivity. It would be much more than that. And then that would diminish with time where it would level off to the saturated hydraulic conductivity. So you could calculate how much volume could have been lost in that period of time by doing some calculations such as that.
Yes, Dan, you are correct. I mean, we suspect infiltration rates considerably higher than the ones that will be on the saturated or even on the dry clay soil because of the cracks that develop in the soil.
Pedro, this is Jeff here. You'll recall, but I'm not sure how many other folk have seen it, that Victor Corinne did a point water balance and point runs of Sacramento-like simulations, and he was able to replicate that second peak. And what the gentleman who just spoke said is consistent with what Victor's conclusions are. We didn't go beyond that point set of physics because we didn't have enough soil moisture instruments and soil temperature instruments out there to be able to do it over a broad area. And I think that the suggestions that came up earlier of trying to get more, not just soil temperature, but also soil moisture probes down in there really is probably going to be necessary to end up solving this problem. And having said that, I've got to tell you, we're going to have to drop off in just a minute, but go ahead.
No, we agree with you.
It might be worth circulating to some of the folk who are on the call a copy of Victor's conclusions.
Yeah, if you have a little bit of a short report, I remember seeing something that he wrote, but I don't have it. But Jeff, you have the Mike seminar coming up, OHD seminar coming up in just now. So I'm going to thank all the participants for coming, for joining us. I think there was a very fruitful discussion. Thank you very much, and we will keep you posted on how we progress on the Red River. Thank you very much, and thanks to very especially for Skip and the Dakota Water Science Center.
Yes, thank you. Thanks, Pedro.